I'm just gonna start recording because I don't want to.
Oh, yes, sure. Let's
Yeah, I don't want to
record.
lose anything.
Sorry.
Well,
Oh, yeah, we're losing
we were
some.
talking business there for a second, but
Yeah. So now we're
now we're
talking.
digging in.
Okay, so we're looking at the data structures in GraphBLAS, SuiteSparse GraphBLAS, of course. Whenever I say GraphBLAS, it has to be prefaced with SuiteSparse. That's just too many syllables. Okay, so this is a kernel that's only doing symbolic analysis for the Saxby3 method. Saxby3 is Gustafson's method, kind of modified a little bit. So it's doing adding columns together. It's sparse times, or so matrix times matrix stored by column. And so I have to go down the column of B and pull out scalars and then set union columns of A together. That's the Saxby method, AX
Mhm.
plus Y, because A is a matrix, X and whatever. So it's Saxby. And it's using Gustafson's method where I need some workspace to do the gather scatter. And I'll either have, there's four variants of this, by the way. There's coarse and fine grain. Coarse, it deals with how the OpenMP tasks talk to each other. There's no atomics. Fine grain, there's atomics. Multiple threads share workspaces and they do stuff with atomics. Coarse grain, everybody does their own thing. But each of these coarse and fine variants have two kinds of workspaces. One is Gustafson style, coarse Gus or fine Gus. Gustafson, that's your workspace is a size n. If you have n by n matrices, your workspace is size n. If you want the ith entry for the ith row, it's in position I. You don't have to go look it up. It's right there. Well, it is a lookup, but it's constant time, no hashing. The other thing is a hash table. The workspace itself is a hash space because you multiply two hypersparse matrices together, n is 2 to the 60. You can't afford any memory space that big. So I built a little hash table for each worker. And now do I share the hash table with multiple threads, or does every thread have their own hash table? Well, if they have their own hash table, it's coarse. So that's coarse hash. If the threads share the hash table, it's fine hash, fine grain parallelism with atomics into the hash table. That is really crazy because now I have to do atomics into a hash table. That's mind-boggling. Okay, so but we're looking here at the symbolic analysis, and that's I think going to it is going to know the difference between coarse and fine, but it doesn't have to do any atomics to get to this point. If I remember, maybe it does. I forget. Yes, it does. Yeah, sorry, it does. I lied. The symbolic analysis has to maybe use atomics as well. Because all I'm doing is counting things. How big is the output? And how big does each task, because I want to glue the outputs together. Matrix multiply is often a multi-phase process. Symbolic analysis says, how big is the thing on output? And I also want to break that into pieces so every task, parallel task, knows where its output goes. So every task has to first compute how much output it's going to produce. Stop, just give me a number. And then cum sum, now every task knows where to put it. So this is the symbolic analysis is just doing this counting. And this is a ton of like fine, this is say the fine hash, this is fine grain. Okay. I'm iterating across this is a fine task. And then I have coarse tasks as well down here. So there's all sorts of different tasks going on. And I can have a mixture, by the way. When you multiply two matrices together, I might decide, oh, there's 5 coarse tasks and 12 fine grained tasks. And a thread will go grab a coarse task and just do it, no atomics, just do it. Have its own workspace. Nobody's going to bother me. And then otherwise, they'll have a team that work on the fine tasks. And then we have to, we iterate across the fine, I iterate across the fine tasks, which is a parallel loop. But when I see a fine task, that means other threads might be accessing the same data structures through atomics. So and I do them all together. A set of tasks, I could have coarse and fine all mixed together. Not interleaved, but I mean, I have a list of both coarse and fine. And so where am I going with this? Where I'm going with this in terms of the data formats. So there's already 4 different kinds of parallelism: coarse and fine and hashed and Gustafson full array workspace. But there is also the matrix format, and do you have the mask or not? See, now this is known at compile time, because this template here, this is a kind of template, but it's not JITted because it doesn't depend on the data type. So I just construct them at factory time with all possible variants, and that's what you saw here. Where am I? All these SAXB3 sim things, there's like, how many of them are there? I can't even count that high. It's all the combinations. Like there's no M or N, so there's no mask in these methods. There's a mask, it's not complemented. And there's the complemented mask with an N. And then the next two letters, this is bitmap and hypersparse. This is full and hypersparse, hypersparse and bitmap, and so forth. But see, they all use, if I look at how big these files are, they're all the same size. They're all just little wrappers around the template that they all use this factory template for the SAXB3 symbolic. This, which is 500 lines of code, but it brings in its own templates as well, I think. Yeah, more templates for that particular phase, which these templates are, they're templates, not factory. These things are used within the JIT because they do the actual work, but there will be a flag in there that says you're not doing the data, you're just doing it symbolically, I think, if I remember correctly, because these course tags don't have to. Oh no, it's a phase one. So I know this is a, wait, template. This just goes into template, or does it need to go there? I forget. I guess it does. Anyway. Oh yes, because in phase one, some of it does depend on the data type. Okay, so it's a lot of variance. It's a ton of variance. How many matrix multiplies do I have? I don't even know how to count that high. I don't even know how to count it. Because do you count these as different algorithms? Yeah, they're kind of different algorithms. Do you have the mask present? Is the mask complemented or not? Yeah, it's a totally different algorithm now. Just for course Gustafson. So for phase one being the symbolic analysis. Oh, but no, it's course hash, or no, it's course whatever. Oops, it's course hash with a mask. And the mask is in place because it's bitmap. It just goes on and on. And this is just for debugging. This is to make sure I did the right thing. I'll often do this kind of thing in my code. I'll have a huge amount of scaffolding code. This is a huge chunk of code. But this just walks through sequentially and says, this is what I just did. I've got all my hash tables set up. I know the counts of things. I know that, yes, I can assert. Like that is a super weird assertion. Why is this the counts of things? What the find tasks have done. They've counted up part of the symbolic analysis. So this assertion is really important. This is all debug code. This is a self-checking debug code. It's not in production unless you turn on debugging. So my point in this is that, oh, let's just toss a new data structure. I can't use that kernel anymore for that data structure, right? I have a completely different algorithm, probably, because I have to walk through in some uniform way this. If I go to the factory and look for this, okay, where do I here? Get the entry from the mask. Where do is it GBI? Actually, yeah. Get a row index. Get, let's see. Oh, It's because I got to go to the templates. You know, get the H hypersparse index for the, well, that could be 4 different matrix formats for B. It could be bitmap, it could be sparse, it could be hypersparse, it could be full. And only if it's hypersparse does something actually happen. Otherwise, J is equal to K. Or, oh, get your row index, please. Okay, let's get the row index. Oh, I guess I don't have it. Let's see. Where's Saxby 3? Oh, I know where it's hiding. Yes, it's because it's hiding inside. Well, I'm going too deep at this point. So if I had a entirely different format, none of these algorithms would work anymore. I would have to have completely different new algorithms for handling these combinations.
Could there be some way of like on demand loading the values into an existing format? I'm not sure I'm saying that correctly. Or like an event fires and triggers a data load into memory, and then you do the existing algorithm.
Maybe. That's a little dicey because some of these algorithms walk through the matrices in random order.
Yeah.
So that's dangerous.
Well, and it involves like, page faulting and intercepting page faults, which can be done, but it's not very portable. It's like sort of a very platform specific sort of thing.
Yeah.
Okay. Yeah.
So
and last week, I think we left off on hyper hashing.
Oh, yes. So let's not dig too deep here. Let's look at hyperhash. Okay. So where we were in the built-in folder, I think, right? So these are all my built-in objects, my built-in matrix, the matrix. This is the matrix data structure, and also the scalar data structure, the vector. It's actually the same thing. It's just gbmatrix.h. Okay. And it's an include file because it's not standalone source code, but it's weird. It's component of a struct, and it's got that hyperhash in it. Okay, it's described here in verbose terms. It's just another matrix. There's a matrix sitting inside every matrix, and it could be matrix all the way down. No, it stops.
All right.
Okay, because this matrix Y is for the hyperhash if A is hypersparse, but it is a matrix that is not hypersparse itself. It's always just sparse. All right. So what is the hyperhash? Here's what it does. It's basically the inverse, and I really should maybe bring up my paper here, although I'm running out of actual paper. If we need this, I'll turn on my camera. I should turn on my camera.
Yeah, if it's easier to draw. Unfortunately, in the recordings, the little side camera is pretty small.
Oh, right.
But I don't know if you could like draw big. I don't know.
I'll try to draw big, or we could, when it's important, we could pin it maybe in the recording. Would it pin it? Would we record the fact that this is pinned and blown up?
I think.
Okay. Well, let me try to describe it without this if I can. So it's an inverse of the hyper list. So the hyper list, let me make this a little bit bigger.
So I just pinned it on my end, but I don't know if that pins it in the recording.
Okay. So if A is a hypersparse matrix, J is the name of the kth vector in the A matrix. So J is AH of K. It's a lookup. So you can iterate through the K vectors, the kth vector. K goes from 1 to the number of vectors you have stored, which is nvec. number of vectors, which could be 10, and the vector dimension could be 1,000,000,000 because it's a billion by billion matrix with 10 vectors in it. So K will go from 0 to 9. J will be the name of that kth vector. K goes from always zero, the first one, the second, the third, the fourth. That's non-empty. Every vector then, well, you could have an empty vector in the hypersparse. Usually I don't. In hypersparse matrix in this set of vectors, but it's the set of non-empty vectors. There's say 10 of them. So AH will be an array of size 10, NVec. But like that's sort of like a matrix that's one, if it's say stored by column. Let's imagine things are stored by column. That's easier to think of for me. So I have a matrix that's 1,000,000,000 by 10. And I'm using that as a proxy for my big matrix. It's actually billion by billion. I say I really kind of store it as 1,000,000,000 by 10. So 10 columns. Oh, but those 10 columns are not the real names of those 10 columns. Column 3 of that matrix is not really the third column. It's column J. The K is 3, J is 100 million. Okay.
Somewhere in hyperspace.
Somewhere in hyperspace, yes. So that's the hyper list. It's not a hash yet. Okay. Now, there are cases in some algorithms, many cases, this is enough because you just iterate through the matrix, you know the K already, you're iterating through the K space, and you just look up J, and you have to go with K and J together. Great, you're done. Other places, you need to go to a matrix and say, give me your J, like give me the vector with name 100 million. Ooh, hang on, I don't know what that is. Oh, it's the third thingy, it's K is 3. You got to invert that, right? I want to find the K given a J. I need the inverse of AH.
Without like searching the whole space.
Well, a
Yeah.
binary search, sure, that worked. And that's what I used to do. I would just do a binary search on this when I need to. And that's what I do still if I choose not to build a hyperhash, I just do a binary search. It works just fine.
But you
Because
want
if
that
it's 10,
O1, you want that O1 cost of
kind of
a hash
close to
table.
01, you'd like to have, and binary searches are bad on CUDA. You do every time I mean, that's expensive. Okay. So I came up with this idea of, well, gee, I could build a hash table, but you see, it's a static, there's no inserts and deletions into this hash table because the hashing is just across the vectors that are present in the matrix. Well, yeah, that's not changing a lot. If the matrix changes, I just delete the hyperhash and rebuild it when I need it. I just delete the whole thing. So I decide, well, okay, cool. How do I store a bunch of hash buckets? Well, what if I have 32 hash? See, I have a hash table of I have 10 vectors. Imagine I have, keep that in mind, 10 vectors, and say I want to hyperhash that. I actually don't because it's too small, and binary search is super fast, so just do it. I have a limit. I mean, if the matrix is so extreme, I don't even bother to build a hyperhash. But if it's got 1,000 or 2,000 columns, then sure, build the hyperhash. So let's just use the number 10 for now. Imagine I have a matrix with, it's 1,000,000,000 by 10. I'm sorry, 1,000,000,000 by billion, but with 10 non-empty vectors. I decide to build a hyperhash. The hyperhash then I want to make it the collisions to be rare, and so I always force my hash table to be at least no more than a load factor of 25%, and it's always a power of 2. So what would that round up to be? 40, so 64. So 64 hash buckets. I'm going to put these 10 column indices into 64 hash buckets. But they're not going to be moving in and out, in and out. Every hash bucket is fixed in size. Oh, I know what that is. That's just a matrix. So there's my hash function, f of j. I take my j space, I hash it into the range 0 to 63. And then that gives me the hash bucket that contains it. So what is this hash bucket? It's a sparse vector of a CSC matrix. It's not itself hypersparse. So what do I want to do here? I have to draw this picture now. So J is
I
AH.
let me try and pin that.
Okay, yeah,
I
if you can
lost
pin that.
I lost your camera. It
Oh,
might be
you
my
did?
bad.
Oh, it's coming up here.
Huh.
I could stop sharing if that's easier.
Oh wait, no, there it is. I had to click.
Okay.
There's these little icons that have no explanation on the. Here we go.
Ah,
Let's try that.
okay.
Okay, so I pinned it.
So now I want to say I want to invert, given J, find K. All right. So what do? I take my A matrix and I build its hyperhash. What does it look like? It's here's the J space is in 0 to what is the dimension? It's the vector dimension of the matrix. So the number of rows in this, now this is a CSC matrix. Y is a sparse, compressed sparse column matrix. And the J dimension is 0 to the vector dimension of the matrix. And it's got 64 columns. And so this entry is Y of J comma F of J, where this is my hash function that tells me which bucket to find it in. And now this is a very sparse vector, but of course it's stored as a contiguous list. It's the hash bucket, and it's sorted by ascending J's. So now if there's a hash collision, I just have to look through there, a very short bucket, hopefully, to find it. Suppose this is 37. Suppose I have 4 vectors that all hash to bucket 37. Then they would all be found in column 37 of the Y matrix, but this particular J might be here. So if I look at this, the 37th column of the the Y sparse column matrix, CSC matrix, I might find 4 entries. So I just have to search that to find the J I'm looking for. That's handling the hash collisions because I have multiple columns, multiple vectors J that happen to hash to the same place. Obviously, I don't want hash collisions. If I didn't have hash collisions, I'd just have 1 entry in every hash bucket.
Yep.
Okay, but maybe I have some hash collisions. Fine. Well, I know how to handle this. This is a sparse matrix. So what is in the column 37 of the Y matrix? It's 2 things. It's a column index, and there's a value there. I actually use this because this gives me K.
So it's
So
like a
I will,
pair. The value
yeah,
is a
it's a, it's
pair.
it's a pair of J and K pair, right?
J and K. Yeah, I got you.
There's J and K. And I already know how to index a sparse matrix. I can do this. It may require a little bit of looking. I compute its hash function that gives me the column it is in Y. And then I just have to look down here and look for J. And when I find J, the value is the K such that J is AH of K. And that's what I'm looking for. If I invert this hyperlist, I want to give a J and find its K. That's the whole goal of this data structure. And I was going to write my own hash tables. I do that all the time, but I'm thinking, well, wait a minute, this is a static hash table. It's just a sparse matrix. Golly, I have that data structure already. Why build me a whole stinking new data structure when I've got one that's just perfect? It's the matrix. That's this is the fundamental idea. Is I have a very, very fast, very stupid hash function, frankly, because it's just supposed to be super fast. Yeah, there could be collisions. Okay. I make the hash table size a power of 2, so I can do bit and operations to mask out, do the modulo thing to know which hash bucket I'm in. So it's a very fast function. And if I have no collisions, then every vector just has a single entry in it, so it's super fast. With a load factor of 2 to 4, um, let's see. This isn't The load factor is 4. Anyway, I'm not sure what I meant by that, but anyway, so here's how, here's the and there's a thing called a hash graph that Oded Green worked on that this is related to. So basically, if this is, once I have the hyperhash matrix, okay, then I can look up K this way. This gives me the number of buckets in the hash table. Okay. And then I get, so it's 64. So I need the hash bits to do the ampersand with. That's going to do the bit map here. Okay. Now what I can do, if I define J, I just have to look through here and look up. I get the hash function and look up. And if I find it, I'm done. There you go. I look at I find if I see the right row index, I just get the value and I'm done. And if I don't find it, then J is not present in the matrix. This will return K as -1 if it's not in the matrix. And so I have algorithms then. Now come back to the pin the code that deal, whoops, I need to make this smaller. Where's my end of my screen here? Okay. So where am I? So the
I seem to have lost the
hyperhash.
code. I have.
Oh, I'm
I see.
sharing still.
Yeah, it's. I don't know what's going on.
So
Oh,
I
there we go.
stop. I'll stop
Oh,
sharing. Reshare.
no, it came back,
Oh,
but
sorry.
oh, it's all good. Yeah,
Sorry.
just reshare. Yeah,
Okay.
cool. Who
So
knows
now you
what will
should
come
see.
out of the recording? Yeah.
Yeah. Okay. So if you go to, I think the hyperhash stuff is here. Yeah. So this is a short little piece of module of the code, 377 lines, because it's just a GRB matrix.
Yeah.
So they're all the other support code to build the thing and so forth. And where do I build the thing? I forget where I build it. I forget who builds the hyperhash because this is looking up the hyperhash. I forget. Anyway, it's going to be. I always build it. There's in wait because I have to do. Wait says finish everything, including if it has going to have a hyperhash, then build it now. So hyperhash, I'm going to build it somewhere, or do I? Where do I build the hyperhash? It's not here. Okay, I have it somewhere. I don't remember where I had it. It might actually just be in here. Okay. Let's just look at all these codes. Hyperrealic, hyperprune. Oh, hyperhash build. That's it. Construct it if I need it. And then the lookup is here. And this is only for debugging because I decided this function is no longer needed. So this is what I used to have to do to look up. I'd have to binary search the H array to find define the thing I'm looking for. Look for the position that gives me there's finally the K. It's a binary search for the position in the H array for what I'm looking for. Okay, this is only for debugging. Now I have a thing called the hyperhash lookup, which is a statically defined function. So it's the hyperhash build somewhere. Where do I have the hyperhash build? Oh, it's not here. Oh, it's probably in the build. It's in the builder folder. Yes, there it is. It probably shouldn't be there. It does call the build. So hyperhash build is really, so I want to build this Y matrix. Given an A matrix, grab its hyperlist and build the Y. And so this is what I have to do. I create building a sparse matrix. I create a bunch of tuples for that with the hash functions. There's my hash functions. And I literally just called the builder. That's it. We're done. That's the whole code. I just build a bunch of triplets. So I have my hyperlist, and this is a parallel loop. So I build my hyperlist, I look up my hyperlist. That's the row index. The column index is the hash function, and the numerical value is the K value. And then build the matrix Y from those tuples. So building the hyperhash is really easy. I've got a builder that does it already. That's why I don't have to write a lot of code to build this hyperhash. Because I use this code for I use this code for GRB matrix build and also building the matrix depending tuples and the same thing. It's an ugly beast parameter wise because it's not exposed to the user. And I ensure that the hyperhash, by the way, is always sparse, not itself hypersparse. It probably is, but just in case. Because I think the builder actually builds it as a hypersparse thing first. It's a hypersparse hyperhash, because that's what the builder does. So I have to convert it here. So building it's not super cheap, but it's a matrix with number of entries equal to the number of non-empty vectors in the matrix. So it's pretty fast. Okay, now once and really I suppose I could have put this function not here, but actually it probably belongs in the hyper folder because its header is in, where is this definition? The code is here, but the definition of the method is here. So it's actually it's in the wrong folder. You see that its prototype is in hyper.h, which is in the hyper folder, but it uses the builder, so I put it in the builder folder. But it's in the wrong place. Some of my source code reorganizing could use a little work.
Well, it's still pretty early in that game too, right?
Yeah.
You're going to do a little more.
You know, the source configuration now in the subfolders is handy, but it's not always perfect. Okay, so this is the builder folder. So let's go back to the hyper folder. Now I need to look up the hyperhash. Okay, so this is the hyperhash lookup. It's a static inline because it's going to be happening all the time. Now I want to say, given if this is true, if J is the kth vector, I want to give it K and I want to look up K. Given J, I want to find the K. Or if vector 110 million is not in the list, I want to get a -1 back as not found. Okay. So what do I have to do to do this? I have the hyperlist already if it's a hypersparse matrix. I'm not passing in the matrices, just the vectors here at this point. And because I've already extracted them out of the matrix and I'm just passing in this static inline function. And so I have the components of my matrices at hand, and I'm going to return K or -1 if not found. And so all I have to do is, oh, whoops, I don't have a hyperhash. Oh, just do the binary search as I did before. Slow, maybe, but maybe it's pretty fast if I have 10 vectors. The binary search of size 10, so who cares? It's not going to be, and even on CUDA, it's going to be fine. This is not a CUDA kernel anyway. Otherwise, I've got to use the hyperhash. So hash it, take the J vector, determine if it is in the hash buckets, it would be in bucket J hash. So that tells me 37 here. Look at column 37 of the hyperhash matrix. And now let's go and look for it. And if J is there, it's going to be here because it's just a sparse matrix held by column. Look in the column. Well, I could have a ton of hash collisions. Do a binary search. This is how many entries are in that column. If it's more than 256, do a binary search itself. Another binary search. Well, why don't I just do the original binary search? Well, this will be rare, for one. And even if I do have a lot of collisions, I've broken them down into smaller hash buckets, most of which are going to be fairly short. If I have a perverse number of collisions, okay, fine, do a binary search. What if in the most perverse case, it's all collisions? Everything fits in the same hash bucket. Well, I should have picked a different hash function. That was stupid, but I don't do that. I have one hash function. Okay, and it's deterministic. So yeah, you can have a perverse case where they all fit in the same hash bucket. Well, then I'm back to the binary search of the whole thing. One binary search. If they're all in one hash bucket, it's the same binary search as I would have had anyway up above if I didn't have that. That's like one hash bucket for everything. There is no hyperhash. So I figured that would be okay because this is rare. Do the binary search. If I find it, that's where it is. Get the K value. Otherwise, just loop, linear time search. Don't even bother. Just look through here. Oh, do I see J? There it is. There's the K value. If the row index is the column J, then I found it. And I found it. What's its position? I don't want its position in the data structure. I want the K value, which is this pair. So my hash entry is a pair of two integers. It's both J and K together. So it's a very simple data structure because I have support for the GRB matrix already. If I want to build the thing, I just call builder. I don't have to have a new hash, to construct a hash table. Looking it up is really simple. And then there, if I find it, there's the start and end of that vector. The K vector, I also return that as well. If it's not found, well, then the vector is empty. So if you're asking, give me vector J, show me its position. Okay, well, its position is -1, and it starts and ends at -1. That means the caller can then iterate from start to end, and well, he'll do nothing because it's an empty vector anyway. So if you want to iterate over this, you'll iterate over some entries. So it's really short and sweet here, this lookup then as a result. And I can still tolerate the fact that there's no hyperhash. This may be determined dynamically. I may choose not to build the hyperhash. And in fact, what Roy was finding in their work with the hypersparse matrices of FalconDB is that I was always building these hyperhash matrices when I had to do a weight. It was too much, and they were often even not needed. So I changed my hyperhash build so that I only build it first of all, I only build it in the algorithms that need it. Like some of the assign methods are going to decide, oh, I need the hyperhash for these matrices because I'm going to do this inverse lookup. Assign does it. Okay. There's the assign methods. Who else does it? Well, the builder builds it, but that's only if it's asked to, right? It's doing it on behalf of everybody else. Who else does it? The add, some of the adds, one of the emolt, this is emolt algorithm 8. One of them needs the hyperhash. Submatrix, the dot product, the SAXP3, just for M&A, not for the B matrix. If B is hypersparse, I don't need the hyperhash, just for A and B. But you see and also weight. So weight is special. Weight, if you call weight on a matrix from the user's perspective, I can no longer change that matrix if I want to see it again. It's now a read-only object for me if it's passed in as an input to a GraphBLAS method. So weight, what happens if you call weight from the caller user level, GRB weight on a matrix, I must ensure that I'm never going to modify that matrix unless you actually change it on output. Then all bets are off, then I have freedom to change it. So I no longer have freedom to change it, so I can't pass it in as an input and then decide, oh, I'd like a hyperhash, because what if some other thread does the same thing? That's a mess. So I can't do that. So zombies, pending tuples, jumbledness, does it have a hyperhash? All those things get decided and done at GRB wait time. But I don't always call wait for the methods that like here's MXM SAXP3. This is the top level CPU host code, not templatized for, whoops, where am I? For the SAXP3 method. This is one of my more complex matrix multiply, sparse times sparse. It's going to present a sparse matrix, and it's going to use the mask as well. The output C is sparse or hypersparse, and the three input matrix can have any format. Full, bitmap, hypersparse, sparse. Okay. And this is the coarse and the fine and the so forth. All that stuff is in this SAXP3 method. SAXP3 is a big method. So hyperhash is constructed. So here, the first thing I come in is I make sure that the hyperhashes exist for the M and the A matrices. And then these things itself could run out of memory. So there's a try catch thing, and this GBOK macro says, whoops, I ran out of memory or some other error occurred, return to the caller, free workspace, return to the caller. That's the try catch in C is with a macro. Sorry. It'd be nice to have true try catches. To have a subset of C, I could, imagine programming this in a subset of C++ is C++ with try catch would be kind of nice. Templates are kind of nice too. All the object overloading I think is overkill, but C++ is in my perspective, kind of a crazy language. It's so many features, but there are some things that I would really love to use, but I don't because it's in C.
And try catch gets into issues of, freeing memory.
Right, but see, I do that.
Yeah, right.
This macro, see if GBOK fails, GBOK works in conjunction with these two macros. If GBOK detects an error, GBOK is defined somewhere up here in these include files. But what it will do is if it detects a failure, it frees workspace. How does it know what workspace to free? Because I've defined this macro. It pulls in this macro to free the workspace. So I define here, this is how I free the workspace, free all. If there's an error, I'll call free all. This is a very common thing across all of GraphBLAS. GBOK on a method. If it works, great. If it doesn't work, I'll call GRB free all and return the info to the caller. And free all frees what? It frees workspace, which is here. Free workspace frees everything but what I wanted to compute, the output. What I want to compute is the C matrix. So free all also frees the C matrix. Although here I'm not actually freeing the entire matrix because the matrix itself is actually a static header. That means the header, the struct that C is for C. It's actually not the user's C matrix. I call it C because that's just handy as the output matrix, but it's actually a temporary matrix I'll slap into the user's C matrix. The header itself is static, so I don't need to do a free on the whole matrix. I just need to free its contents if I have a failure. And I have a method called fibix free, which frees the P, H, Y, B, I, X parts, or fibix free. Y is its hypersparse matrix. The other five, H, PHBIX are just standard arrays inside the header of C. Y is itself a matrix, a hyper hash of C, if it has one. It won't have one at this point for this problem. So the hyperhash ensures that if I want it, it builds it. Now the hyperhash build, though, if I look at builder GB hyper, nah, go away. You don't need it. You're being too much. You don't really need. You're fine. When do I not need it? Hash need. Well, here we go. When do you need it? If you don't have a matrix, you don't need a hyperhash. It could be that it's an M matrix. The M is null. Fine. You don't need a hyperhash if it's the matrix null. If the matrix is not hypersparse, don't build it. Okay. If it already has a hyperhash, don't build it. If otherwise, I'm not going to build it. This, I think, is by default. This is a global settable parameter that you can set with grb get and set. It's, I think, defaults to 1024. Okay, what this means is if the matrix has more than 1024 non-empty vectors, the hypersparse matrix has that many stored vectors. In other words, this AH array is of size 1,000. That's a big binary search. Let's make a hyperhash. And so I return true if I have more than that number of vectors. So all this function is doing is telling me, do you really want a hyperhash? Do you need it? Yes or no? That's all this little helper function is doing. It's very simple. And these decisions are simple. You already have it, or you'll never need it, or you already have it, go away. You don't need to build it. Now the matrix is hypersparse and has no hyperhash. Let's decide whether to build it, and that's the threshold. That's the test. I have a future tag here. This grb get and set is only for grb global get and set. There's one number, 1024, you can change to say all my hypersparse matrices will have the hyperhash if they exceed this one threshold. It's not a matrix by matrix threshold, but it could be in the future. I just haven't bothered to make it that. It hasn't seemed to be worth it, so I haven't done it yet. But I could do that. So what that means, though, is that the hyperhash build might decide, yes, that's a hypersparse matrix. You could, in theory, build a hyperhash for it, but why bother? You've only got 10 vectors in there. Just do the binary search across the 10 and you're fine. And it'll be fast enough. So there's a point at which that hashing doesn't pay off in terms of performance. But the algorithm will work either way. It's just a heuristic. It's deciding when to build it or not and what impact it has on the subsequent algorithm. The subsequent algorithm will work either way because the hyperhash lookup, if it doesn't have the hyperhash, it just does the one binary search. So that's the hyperhash.
And so the trade-off is like build time versus binary lookup time.
Well, it's build time versus binary lookup time, exactly. And it's also even the lookup time. I mean, you've got this matrix. Sure, it's hashed into smaller buckets and you have a shorter binary hash, but what if you're just doing 10 vectors? A single binary search across 10. Search a list of size 10 with a binary search. That's no time at all. You won't notice the difference. So it doesn't buy you anything to build this hyperhash anyway.
Right.
So there's a trade-off, and there's a point at which it really is important. So then this you see this use of the hyperhash build. Then I have this in these various places, and it's not everywhere. I don't build it everywhere because if I look for hyperhash lookup, you see that's it across hundreds of files. When do I need it? Okay, I only need it in gosh, only four. There's zombie assignments. These are GRB assigns that are only assigning zombies into the matrix, and there's 5 different ones, I think. There might be 4 because I no longer. Oh, I have a zombie 4, and I have a sub-assign zombie. You can assign zombies. You can insert if you know you're inserting only zombies into a matrix. Why is this not moving? What? My screen died. No, I can't move this terminal around. What is going on here? No, kill it.
When would you be assigning a zombie?
I'll show you. I could show you. You could have a GRB assign, say assign scalar into matrix. Okay. It's a scalar expansion into a matrix. What if that scalar is empty? The only thing you're doing is deleting entries in the matrix. That's a zombie
Okay,
assignment. That's killing entries in a matrix.
I got you.
Sorry, my I don't know if the screen share or something didn't like that. So so the zombie assign, I don't know, assign it a huge beast. Here, this is delete all entries in a single column. Zombie assign 1, and it's a very special case of an assignment. Zombie, delete all entries in a row. Delete all entries for C replace. So this is zombie 3 has to handle this replace method. If I have a zombie, if I find something and it's zombie, make it a zombie. But all of these zombie assignments, apparently many of these zombie assignments, and yeah, 96 variants. Oh my goodness. There's so many possible combinations of algorithms. It's just crazy. But let's look for that act-l hyperhash lookup. So these are the methods and the templates that need the hyperhash lookup. A lot of the assigns themselves use it indirectly. So this is definitions for all of the assign methods. So maybe more than just those assigns actually have to do the lookup. But element-wise, like remove a single element, extract a single element, order 1 work. There's some work that has to be done. The EYs add, EYs multiply that need the hyperhash. The extract methods, GRB extract, not tuples, but just extract. And then 3 of the matrix multiply methods need the hyperhash. The Saxby3 method and also the .3 method in phase 1 and phase, I guess this is phase. This might be a comment, I'm not sure. But it's very this is itself a macro. So I may use it more spaces than you see. The same thing with this. So this has to do the hyperhash lookup for the mass matrix and for the A matrix, but not the C matrix and not the B matrix. So, and so GraphBLAS has a ton of algorithms. I don't need it all the time. What this means is when I construct a hypersparse matrix, I do not immediately build its hyperhash because I may not ever need it. Either it might never need the hyperhash because it's so sparse. The hyperhash is less than the number of vectors less than 1,000. So I just do a binary search across 1,000. entries, or I never need to use these. Maybe I don't use these algorithms on that matrix, so I never build its hyperhash. So that's what the hyperhash looks like. Now, when I added this data structure to the matrix, I realized I need something else to go along with this, because see, I have this pack unpack mechanism, right? You want very fast access to the matrix. You can at the user level application, not inside GraphBLAS. GraphBLAS inside doesn't need to pack unpack. It has full access to the objects. But at the user level, pack unpack sometimes needs to pull out the content of the matrix in a non-opaque way, work on it, and then maybe put it back. My first cut was oh, you have a hyperhash and you want to unpack that as a hypersparse matrix. So I'll say, oh, fine, you don't have I delete it. Well, then if you pack it back in and I need it, we have to rebuild it. That's expensive. So I added an unpack hyperhash. If you're really desperate to preserve my hypersparsity matrix object, you can unpack it as a hypersparse matrix and also unpack its hyperhash, keep it, fiddle with it, and then put it back nicely. And then I've got back to where we started. It's a little bit delicate. Pack unpack is funny. It's an attempt to provide constant time interfaces to other applications, and also to give potentially some algorithm fast access into my data structure in a non-opaque way. So there's a boundary in which I unpack. You say, here it is. Well, if you unpack, and you have to ask for the format you're unpacking in. What if the matrix is hypersparse and you want to unpack it as sparse? I'll have to convert it. And I'll do that and give it to you like you asked. So that took work. Maybe a malloc and copying and moving stuff around. That took work. And if you pack it back, now it's in a new format, so that's a little friction. But it's opaque. I don't break opacity. It works if you ask for a format that it's not in, pack unpack. It just works. It's a little slower. So it's grease lightning if you unpack it just the right way. And you can ask me what my format is. You can do a GRB get to ask me what format it is on any given matrix. Then you can unpack it accordingly into that format of that data structure. Now, what this means in terms of adding a new data structure to the pack unpack, I don't know. Would we want to then allow an unpack in some other format, like a Stinger style format, an array of B trees? If it's in that new format and you want to keep it in that format and you want to have fast access it in a non-opaque way, then yeah, that would be needed.
Interesting, because it might not be like contiguous like an array.
Yeah, it would be some array
Scattered
of
about.
Scattered about. It'd be an array of pointers to blocks, and each block contained a pointer to other blocks. Maybe it'd be like an array of B trees or something. It'd be its own little data structure. I have a folder on pack unpack. You can do pack unpacks in whatever format you like. But you see there's a pack unpack hyperhash now. And the reason I added it as a separate function, I should have added it to the pack unpack hypersparse, but I didn't want to add those new parameters to the API to say, here's your hypersparse matrix. Oh, also here's your hyperhash. Didn't have it in my original unpack. So I could have broken the API and gone to, a not backward compatible unpack method. I thought, no, let me not do that. Let me have two unpack methods, one to unpack the hyperhash, the hypersparse matrix, and one to unpack the hyperhash. That's what I decided to do.
And they'll be consistent if you call them sort of back to back.
Yeah, you call them back to back, you get what you expect. Yeah.
Yeah, okay. I got you.
It's a little weird. Pack and pack is a little weird. And that's why it's kind of dangerous to add pack and pack to the spec. I'm not really sure how this fits nicely with the spec, especially this weird stuff like a hyperhash. What the heck is, good luck trying to add that to the spec.
Right. Yeah.
Right. It's like, Standard formats, sparse, full, bitmap, nah. Is import export, it doesn't have bitmap. These are GRB imports, exports. GRB, where's GRB export? Yeah, it only has a handful of formats it supports. I don't even think it supports full, which is annoying. But it's a copy out, copy in kind of thing. And so it's always going to take more time than pack unpack.
Cool. Well, do
So
you think this is a
that's the
good,
hyperhash.
yeah, do you think this is a good stopping point on the hyperhashing?
Yeah, I think that's it for the hyperhash. And if you go again, if we go back to where we were with the GB matrix data structure for the hyperhash, it's all fully described here. That's it as a single matrix. And then the support methods are here. And okay, the freeing of the hyperhash is in the matrix folder. All right. The creation of the hyperhash is in the builder folder. Okay. Maybe both of those should be in the hyper folder.
And convert is, oh, I see, any hyper disparse. Yeah, okay, gotcha.
Okay, so the conversion, this is different. This is actually, this is a good point in which when you're talking about the different formats, I have a notion of called conform. A conform is I do some computation, I produce you an output matrix, and I'll produce it in the format that's most natural for that problem definition. Okay, like maybe it's natural. The builder, for example, always builds a hypersparse matrix, no matter what. And then say matrix multiply. Oh, if the inputs are, it'll build a sparse or hypersparse, or it'll build a bitmap, it'll build whatever. When I'm done building it, though, I look at this matrix and say, is this the right format for the matrix? And this is the conform step. You see, I look at the matrix and I say, well, this matrix has potentially 4 different formats I can automatically choose between. Now, that may be reduced by GRB set. You might say to a matrix, you can only be 2 of those formats, not all 4. Then I'll make an automatic decision between those 2 formats you let me do it in. And I almost always follow these rules with one exception. If you tell me this matrix can only be full, I'll say, yeah, right. If all the entries are present, fine, it'll be full. But if there's an entry missing, I cannot store it as full. It is not permitted because I can't just pad entries to make them present where they're not present. GraphBLAS must always respect the structural computation of its result. You always have to say it's not there, it's there, and you get the right answer. Like think of the structural mask. Okay, I can't just stick an entry in there because then the structural mask will say, oh, it's there. No, it's not there. Okay, so if you do a GRB set on a matrix and you say to me, this matrix can only be full, I say, yeah, right. Well, it can be 2 things, bitmap and full. It's the closest I can get. Otherwise, this option, there's 16 combinations of it you can turn on and off. By default, they're all on. And then what I do then is I have this notion of called conform, where I can say to the matrix, okay, I'm done computing this matrix. Let's conform it to its desired sparsity format, one of the 4. And I may decide to convert it then between the 2. And that's what these conversions do. And there's a bit of hysteresis in there because if there's a boundary between sparse and hypersparse, and it's a sharp boundary, and I gain a few entries, lose a few entries, gain a few entries, lose a few entries, I don't want to keep thrashing across that boundary. So there's a hysteresis that if you're in the middle here, if you're already in one format, I'll leave you alone. But if you start moving this way, oh, I'll convert you. And then if you're in this format, oh, I'll keep you until it gets so sparse, oh, you're hypersparse. So there's a significant hysteresis in the middle where I'll keep it in its format. But otherwise, the matrix format is chosen dynamically with this conform process. So what this can mean, it can mean, for example, if you do A times X, A is a sparse matrix, X is a dense vector. You would expect, in some libraries, you expect the output to be a dense vector. Well, that's not true in GraphBLAS. Because if A has an empty row, the output must have a missing entry in it. You cannot fake it and stick an entry in there. But what if it happens to? Like you have no non-empty rows. Well, I have to compute that fact. I'll produce a vector y equals ax, let's say. I'll produce an output y, GRB vector w, whatever it's called in the spec, it doesn't matter. Y equals a times x. I'll compute a vector y, and then I'll look at, oh, look, vector y, you're full. Oh, I convert it to full by just freeing its, if it's sparse, a vector, say, oh, you're full. I'll just delete its integers, and there you got a full vector, just with a free. It converts sparse to full. That's sparse to full. Where is it? And convert. So these conversions, if I go to convert, these are all the codes that handle the conforming and converting. Conform is a heuristic that's saying, well, which do I convert to and from? And then the actual workers do the actual conversions. Like this does do a full matrix to a bitmap matrix, full stop. It always does. It may or may not be chosen based on the conform. So I've convert and conform here in the convert folder. Oh, where am I? I'm in the convert folder. And I have some templates as well because I don't think I may actually have a JIT wrapper for the conversions. Yeah, one of the converters uses a JIT. I need more JITs for these, some of these, I think.
Is that sparse to bitmap?
Yes, because I have to move data.
Oh, I see.
Yeah,
Yeah, okay.
I have to shift data types around. Because if I have to expand it, the data, and rather than doing a mem copy, I just want to do an assignment. This method here is different. If I'm converting full to bitmap, I don't move any data around. I just make a bitmap that's all true. If I'm converting full to sparse, I don't move the data around. The full matrix stays full. I just add all the integers.
Mm-hmm.
See? The same thing if I convert a matrix from full to sparse, or no, sparse to full, sorry. A matrix going from sparse to full means that all the entries are present in that sparse matrix. Oh, so I just free the integers and I'm done.
Right.
There's no movement of the data. So I don't need it templatized. I don't need versions for every data type. But if I need to move the data around, okay, now I need a templates to do that. S to be sparse to bitmap, I guess. Then I need to move the data around. Sparse to full, I don't move the data around because I can't, and there's no need to. You only convert to a full matrix if all the entries are present. If you have a sparse matrix where all the entries are present, then its numerical array is the full matrix you are looking for. It's already there in the right place, the right pointer, the right dimensions, the right stride. You're done. All you do is free those integer arrays and you've got your full matrix. But you see what that means is when I compute y equals a times x in GRB VXM or MXV, you may look at the output and say, oh, cool, thanks, Tim. You computed me a dense vector as I expected. Yeah, because I had to check that case. Because I had to build it in a sparse form or a bitmap form because I didn't know until I looked and I said, oh, it is actually full. I'll throw that away. I'll throw the integers away. See, that took me extra time to do. But I have to do it because that's what the spec says I have to do.
Mhm.
The fix for this, if you will, if you want to insist on an output that's dense, then you have to give me an accumulator. You have to do y plus equals sparse times dense, let's say. Or y starts as dense. And now that there's an accumulator, I can assert that there shall be no deletions, because if there's an accumulator, there's no deletions. So now I know the output will be full, and I don't have to compute the output. So to do that, then I have a separate kernel for that. And that's like the Saxby4 method. See, this is full plus equals sparse times full. Well, sparse or hyper times bitmap full. That's Saxby4. Or I'll have, I think Saxby5 is the opposite. It's C plus equals A times B, where A is bitmap full, B is sparse or hyper. It's reversed. So the order, the algorithm is slightly different. So that's a different algorithm. And it can exploit the fact that I know the output starts full and stays full. And I can write directly into it as well, because I only use those algorithms if the accumulator matches exactly the monoid. Then I can just accumulate and do the monoid right into the output vector or output matrix, actually. So, yeah, so those, I'd say, I think everything about the data format. And you can kind of see just, I mean, looking at just the matrix multiply wrapper, you know, it's a beast of a code.
Do you think we should dedicate the next session to looking at
Matrix multiply.
MXM? Yeah.
We could do that. Yeah, we
I
could do
mean,
that.
and it sounds like one session isn't enough. I mean,
No, it won't be enough because
just sort of like the high level,
mm-hmm.
go down one or two levels and then
Yeah,
see where we're right there.
there's a big distinction between the Saxby style and the dot style. You can see the dots here. There's
Yeah.
AXB dots. There's various dot product methods, and there's various Saxby methods: Saxbit and Saxby3, Saxby4, Saxby5. I ran out of names. I ran out of imaginations. So I just called it and there's no Saxby1 or 2 because those are old algorithms I deleted. So I just, I didn't rename. I just kept going. The dot one is gone too. There used to be a dot one, I think. Dot two was the second one, and now dot one is gone.
Mhm.
So yeah, matrix multiply would be a good thing to look at next.
Or if you think there's an intermediate step between where we are and multiplication.
Well, the intermediate step might be to look closer at the JIT. Because when I hit the MXM, we're going to be talking to the JIT a lot.
That's true. Yeah.
So how does the JIT work? How does the JIT handle? How do I construct these JIT kernels and compile them? Where do the codes come from? Where do the templates? Well, you look at the templates. Like these template files are also used to build the JIT kernels. If you see a folder called template, that means it's source code that's used for both the factory kernels and the JIT runtime kernels. So there's a lot of codes there, but how do I decide? I mean, how do I construct these JIT kernels to use these templates? How do I compile my templates? Well, when you compile a template, you have to define what it is, the data type. What is the operator? What is the add? What is the multiply? What matrix format are you in? How do I get the row index of the matrix? Do I do a mod if it's full or bitmap? Do I look up the integer, whatever, the AI array, the integer array or whatever? I mean, if it's sparse or hypersparse. And so there's macros that access that I showed you already. There are macros like, well, give me the monoid identity value. Give me a scalar with a monoid identity in it. I have to define what that means. add two numbers together. Add what via the monoid. Oh, how do I do? Well, that depends on the monoid. How do I specialize my templates to be able to compile them into a specific kernel? And how do I then decide, if you call me again, that I got the same kernel? See, I have to, there's this enumeration space. Actually, I call it enumify. I made up words, verbs, with all of them have phi in it. If I look at the JIT, the JITifier, this is the JIT. All the functions have the word except for this one. This is file IO stuff, but I only need it from within the JITifier, so I put it there. All these functions and all these files have the letters FY in them. Encodify, enumify, macrofy, build the macros for this JIT. This is the master right here function, JITifier. This has got a whole bunch of methods in it. Actually, you can see it's a big file. And so enumify and codify. Enumify is a very specific thing. It says, for example, I have the case of MXM. I need to set 63 bits, it turns out, to give me all possible instances of MXM. Why is it 63? Well, I could show that to you next time. But already 16 bits of the 63 is taken up by the 4 matrices deciding on what is their format. Are you sparse? No, that's not 16. That's 2 bits apiece. There's 4 cases for every matrix. That's 8 bits, sorry. Because there's 4 matrices. Each one of them has 4 formats they can be in. So it's 8 bits already out of the 63. You see, I have to this enumification has to happen very quickly, because if you call the kernel again, if you call a kernel and I don't have it, fine, that takes a long time. Got to go load it from disk. Oop, I can't load it. Oh, I got to go create it, write the source file, go compile it, then I'll load it in, and then I hash it in my hash table of JIT kernels, and then I can get the function pointer, and there. Okay, that took me 5 seconds. And you call it again, I have to take the instance of the call, and I had to figure out its enumification to know, oh, I've seen you before, and then you're here in my hash table. I have to then encode it, enumerate it, encode it so then hash it, look it up, give you the hash function, call the hash function. That has to happen very fast, because it's every time I'm looking up that function pointer in my hash table of all my JIT kernels. That has to so the space of all possible, and then how do I then create the macros and encode these things? Creating the macros can be slow. I only do it at compile time. But still, the enumeration has to be done very fast. And so this handles all of that. So the JIT is a big beast as well. And the JIT is important to understand. It's of course, JIT's the whole GraphBLAS. Right? It JITs the MXM, it JITs the reduce, it JITs the select, it JITs the element-wise add, element-wise multiply, and so forth. It JITs the encoding, the reduction to scalar, say. And it does this for both all this JIT here you're seeing works equally, almost identically for CUDA JITs kernels and OpenMP JIT kernels. It's almost the same. The same set of macros, it's almost identical. There's very little differences between them. The header is the same. There could be like an if-def CUDA kernel. Oh, if-def your CUDA, do one thing, if else do the other. Otherwise, it's very, very similar. So the JIT's really important, and it also ties into what it is. MXM is huge. This is MXM. It doesn't even fit on the screen. It starts here. This is MXM. Right, it's massive. I wish it wasn't so complicated, but I mean, it's a complicated algorithm.
Yeah, okay. Well, I think you're right, starting with the JIT then for the next session.
So yeah, maybe the JIT, because once you see the JIT, then some of these specializations, when you look at this kernel, it'll have a macro that tells me, oh, there's the add operator, there's the multiplicative operator, and so forth. There's the data type. And these are all templates where they're C templates. So what's a C template? Pound define macro, pound include source code. That's a template. And how do I build that? That's the JIT, right? Oh, or how do I build it at the factory time? Well, that's also pound and find macro, pound include, but I do that at development time, not at JIT time. So I think that the structure of the factory kernels, the structure of the JIT kernels, and how the JITs, how they work together actually, is really important. And then how the CUDA JITs tie in that as well. It's all a big spectrum. That might be more important than the specifics of MXM, because once you hit MXM, you'll see all these macros. Like, where do they come from? Oh, they came from, say, the JIT build them. Well, let's look at the JIT then first. That might make more sense. Does it sound like a plan?
Yeah, sounds good. Yeah.
Okay.
All right. Well, Tuesdays seem to be working pretty good for us. I don't know if that's still pretty good for
Yeah,
you.
Tuesdays in general are really good. They're wide open for me. So we could plan the same time next Tuesday.
Here, I'll stop the